So here the next part of the discussion is that is preparation and properties of ammonia. Preparation and properties of ammonia. If you take ammonia, this ammonia has interesting characteristic features. Ammonia, it can act as a Lewis base and also it can act as Bronsted base. It is an associated liquid. It is an associated liquid. It can also exist in the form of a covalent solid. So if you take Lewis base, it is acting as Lewis base because it contains one lone pair of electron. All the species or all the molecules which are electron pair donors are Lewis bases. So that's why we can say that it is acting as a Lewis base. It's a good electron pair donor. That's why it's a Lewis base, and all the molecules or species which are good electron pair donors are said to be Lewis bases. And it is also a Bronsted base because it accepts a proton. According to the Bronsted-Lowry's theory, ammonia molecule also accepts a proton, and it is going to give a conjugate base. And because ammonia molecule it is an associated liquid, it also shows the hydrogen bonding. On cooling this ammonia, this ammonia gives, that is crystals, ammonia crystals we get. Ammonia crystals can be obtained upon cooling. That's why we can say that it also exists in the form of, that is, covalent solid. So now what is happening here is, let us give proof for that why ammonia can act as Lewis base and Bronsted base. So for example, if I say ammonia is acting as a Lewis base, if it is LB stands for Lewis base, yes, it donates a proton. So here the proton is acting as Lewis acid. So this proton behaving as a Lewis acid, it accepts a lone pair of electron from ammonia, and it is going to give a new species, that is ammonium ion. So this equation indicates that ammonia is perfectly acting as Lewis base. So next, if you're taking ammonia, same ammonia you take, and it can act as a Bronsted base. If it is acting as a Bronsted base, yes, it's a proton acceptor. If it is a proton acceptor, then it is going to give the ammonium ion. Then Bronsted base always gives conjugate acid. So therefore we can perfectly say that here it is accepting a proton. The ammonia molecule acting as a Bronsted base, it is accepting a proton. So that's why we can call it as the Bronsted base, and the residual species which we got here is treated as an ammonium ion. So if you take conjugate acid base pairs, ammonia of NH4 plus, this is going to become the conjugate acid base pair, conjugate acid and conjugate base. This is what you need to keep it in your mind. So conjugate acid base pair has been formed. Yes, ammonia, if you take, it can form the hydrogen bonding. So therefore it can be treated as associated liquid. That's why it is highly soluble in water, and it has high boiling point. Then ammonia upon cooling, it is going to give a covalent solid. These are all the important properties of ammonia. And so here, if you take this ammonia in particular, if it undergoes self-ammonolysis, if you take ammonia molecule plus ammonia molecule, if you take reversible reaction, it is going to give, that is NH2 minus plus NH4 plus. So that means this is nothing but one is acting as conjugate acid and the other one is acting as conjugate base. So if you are treating this as Bronsted acid, and one is treated as Bronsted acid and one is treated as Bronsted base, so it is going to become Bronsted base. So here if it is Bronsted acid, then it is going to lose one proton and it forms NH2 minus. So for this Bronsted acid, the conjugate base, this is the conjugate base, and for this Bronsted base, this is the conjugate, that is acid. So this is called self-ammonolysis. Apart from this, if you go for the normal laboratory preparation, that is preparation of ammonia, there are many methods of preparing ammonia. So preparation of ammonia, if you take particularly, you can take preparation of ammonia by treating the salts of ammonia with calcium hydroxide also we can prepare. But first one, the very popular preparation of ammonia is, you take urea and you subject it to hydrolysis, then you are going to get here, that is ammonia. here the urea, this is NH2CO, NH2 is urea. Urea upon hydrolysis it gives ammonia, and it can give, that is carbonic acid. So that means you can easily understand that how it is going to form, because we have actually two nitrogens are there, so take 2 over here, and yeah, we have 6 plus 2, 8 hydrogens are there, and we have 3 oxygens. So I think if I am going to take 2 over here, the rest of the reaction is going to get balanced. So we got carbonic acid. Carbonic acid is a weak acid, and ammonia, if you take, it's a weak base. Okay, ammonia is a weak base, so therefore ammonium hydroxide, actually ammonia plus water, it is going to give ammonium hydroxide. Ammonium hydroxide is obviously a weak base. Anyhow, this is an aqueous solution. This ammonia exists in the form of ammonium hydroxide. So this is one method of preparing the ammonia. Then go for you take ammonium chloride. And you can treat it with the slaked lime. If you are treating ammonium chloride with slaked lime, yes, you can get definitely ammonia gas. Then you can get calcium chloride as a byproduct, and H2O, that is 2 molecules of H2O. Yes, we have the number of chlorines are 2, so therefore better if I take 2 over here and 2 over here, the reaction is also going to get balanced. So 2 moles of ammonium chloride reacts with 1 mole of slaked lime to give 2 moles of ammonia and 1 mole of calcium chloride and 2 moles of water we are able to get. And also we can add one more preparation here. For the same ammonium chloride, if you are going to add a strong base, then you are going to get here ammonia plus sodium chloride plus water. You know very well that if you take ammonium chloride, for that matter, I can say that this ammonium chloride is a salt. It is a salt which is made up of the weak acid plus strong base. So therefore when you are adding a strong base to this is a strong base, and it's a salt of weak acid and strong base. Again it is going to give this ammonia and water, in turn they are going to react, and it is going to give a weak base, and it is going to give a salt of strong acid and strong base. So that means salt, when it is subjected to salt which is treated with a base, it has to give back the salt, a new type of salt. It is going to give salt of strong acid and strong base, and of course weak base also it is formed, that is ammonium hydroxide solution. So altogether we have given 2 or 3 important methods we have done in the laboratory method where we can prepare the ammonia. Now in the large scale, if you are going to the large scale preparation, for example, large scale preparation, if you go for the large scale preparation of ammonia, this is not a new process, it's very familiar process for us. So in the Haber's process of ammonia, in the manufacture of ammonia through Haber's process, if you go for Haber's process, if you're going for the Haber's process, this Haber's process follows the Lee-Chatelier principle, wherein which it follows the Lee-Chatelier principle, and in the Lee-Chatelier principle, it's the formation of ammonia is always exothermic process. Then when it is following Lee-Chatelier principle, suppose if I am going to write the equation N2 gas plus 3H2 gas, N2 gas plus 3H2 gas reversible reaction 2NH3 gas plus 46.1 kilojoules per mole of energy is actually released during the formation of 2 moles of ammonia gas, and definitely it is following the Lee-Chatelier principle. When it is following the Lee-Chatelier principle, we are finding that here you have total number of volumes are 4 volumes, and here you have 2 volumes. Here you have only 2 volumes in the product side. So when it is having 2 volumes, when the volumes are decreasing, then automatically there is increase in the pressure, decrease in volumes from reactants to products during the establishment of equilibrium between the reactant molecules and product molecules. Decrease in the volumes will lead to increase in the pressure, which is in accordance with that is Lee-Chatelier principle. And because it's an exothermic process, the enthalpy change is going to become delta H is equal to minus 46.1 kilojoules per mole is the energy. And what are the reaction conditions for the large scale preparation of ammonia through Haber's process? So if you go to the reaction conditions, I can say that here catalyst is Fe2O3 is the catalyst, and you can add promoters like a K2O is the best example of promoter, which is going to increase the activity of catalyst. And the temperature is, if you go to the temperature is not less than 700 Kelvin. 700 Kelvin is the optimum temperature, and the optimum pressure of 200 atmospheres of pressure we maintain. Under these conditions, the yield of ammonia is quite significant. and this leads to the formation of ammonia through Haber's process. So this is the manufacturing method of ammonia through Haber's process. So here if you go to some additional properties of the ammonia, that is, if you go for additional properties, that is structural aspects of ammonia. If you take ammonia, if you go to the structural aspects of ammonia, this is like we have 3 nitrogen-hydrogen bonds and it has 1 lone pair, and it is something like pyramidal in shape. So you have here, that is nitrogen, here nitrogen undergoes sp3 hybridization, but its geometry or shape is pyramidal. Its bond angle is 107 degrees. Bond angle is 107 degrees. The decrease in bond angle from the 109 degrees 28 minutes to 107 is because of this is the molecule is distorted. The molecule is not a regular molecule is distorted. If it is distorted, that means lone pair to bond pair repulsions are greater than bond pair to bond pair repulsions. That is why you can see that the bond angle in ammonia can change from 109 degrees 28 minutes to, that is 107 degrees. Apart from this, if you take ammonia, that is go for the ammonia. In this ammonia you can see that the lone pair is at the apex of its shape, that is pyramidal shape, and if you go to this ammonia can be dried. The impurities present in the ammonia impurities can be removed by passing over quicklime. That is, in other words, ammonia can be dried. It can be dried over quicklime. This can be dried and separated, dried and filtered. And ammonia cannot be dried. Ammonia gas cannot be dried. Okay, it cannot be dried over. That is calcium chloride or that is sulfuric acid, because the ammonia reacts with both these compounds. It can react with calcium chloride and it can also react with that is sulfuric acid to form the respective, that is, compound. So for example, ammonia when it is reacting with calcium chloride, ammonia when it is reacting with ammonium hydroxide, ammonia plus water gives rise to ammonium hydroxide. Ammonium hydroxide in turn reacts with calcium chloride to give ammonium chloride plus water. This is unwanted reaction which we are going to get in the case of the calcium chloride. Similarly, same ammonium hydroxide, in the similar sense, same ammonium hydroxide, if it is going to react with sulfuric acid, so it is going to give, that is, ammonium sulfate plus H2O. This is also an unwanted reaction. So ammonia cannot be separated or cannot be dried once it interacts with calcium chloride or calcium sulfate, but ammonia cannot react with that is quicklime. It cannot react with quicklime. That's why it can be dried over the quicklime and it can be separated and it can be filtered. So this is one of the important aspect of ammonia which we have to keep it in our mind. Ammonia, apart from this ammonia, it forms precipitate, that is test for ammonia. So when it is reacting with the zinc chloride, ammonia molecule, when it is reacting with zinc sulfate, for example, if you take, that is, ammonia plus water. So zinc sulfate, when it reacts with ammonia in the presence of water, it can form that is zinc hydroxide. It forms white precipitate plus it can form ammonium sulfate. So you can see that it is giving a white precipitate. Likewise, that means ammonia is going to give a white precipitate with the zinc sulfate. Then go for ferric chloride. Ferric chloride, when it is reacting with the ammonium hydroxide, because ammonia dissolved in water is ammonium hydroxide. So you can just take this as ferric hydroxide. This is brown precipitate, brown PPT, and it forms ammonium chloride. Ammonium chloride. So take 3 here and take 3 here. It forms a brown precipitate. 2 tests are completed. Then we'll go for one more. That is, if you take copper sulfate, if you take it reacts with the ammonium hydroxide and it forms CuNH3 taken 4 times of, that is sulfate plus H2O. You can take H2O if you are taking, then I think if I am taking 4 moles of ammonium hydroxide, if I take, there is 1 sulfate, 4 ammonium ions and 4 hydrogens and 4 oxygens. So therefore if I am going to take 2 here, so this is going to become tetraamine copper sulfate. It's a complex tetraamine copper sulfate which gives the blue color. So blue color complex, it forms a blue color complex, tetraamine copper sulfate complex. It's an cationic complex. It's a cationic complex where the sulfate is anion outside. It forms a cationic complex. Then likewise you can take one more, that is D. If you take silver chloride, if you take silver chloride aqueous and when you treat it with ammonium hydroxide, it forms a precipitate, that is AgNH3 taken twice of chloride plus H2O. So here we have 2 ammonia molecules. So take 2 over here and take 2 over here. The reaction is going to get balanced automatically and it forms diamine silver chloride complex. It is a white precipitate. It forms a white precipitate complex. So these are the different types of tests where we can notice. So here the next part of the discussion is, that is preparation and properties. Preparation and properties of, that is nitric acid. So if you go for preparation and properties of nitric acid, actually the formula of nitric acid is, that is formula of nitric acid is HNO3. It is this nitric acid, it's this HNO3, it has it's a strong acid. It is a strong acid and it is a highly oxidizing agent, highly oxidizing in nature. Highly oxidizing in nature. It has a specific gravity of 1.504 grams per cc. Then if you take this nitric acid, if you are taking this nitric acid particularly, it is soluble in water. Its solubility is high and in gaseous state it is a planar molecule. And for nitric acid solubility is high, in gaseous state it's a planar molecule and it forms constant boiling mixture. It forms a constant boiling mixture. It forms a constant boiling mixture at 68% by mass. 68% by mass, and it can be concentrated at 68% of purity, 68% of weight per volume. It becomes it can be increased. Its purity can be increased. Now the purity, if it is 68%, it can be increased. The purity can be increased by adding concentrated H2SO4. If you add, the nitric acid purity is increased up to 98%. So at this particular 68% by mass, it becomes the constant boiling mixture. This constant boiling mixture, we can call it as azeotropic mixture. So if you go for preparation, if you go for nitric acid, yes, this nitric acid, because being a strong acid, HNO3 aqueous plus H2O aqueous, immediately it is going to give one H3O plus ion, it is going to release one proton, and it is also going to give one nitrate ion. Fine. So if that is the case, if you go for preparations, if you are going for preparation of nitric acid, you can take potassium nitrate when treated with sulfuric acid. Yes, you can directly get nitric acid plus potassium sulfate. You can get directly nitric acid, or else you can also get the nitric acid. The same nitric acid you can also prepare in the laboratory through Ostwald's method. That is through Ostwald's method. You take ammonia as a raw material, take the ammonia gas as a raw material, and for this ammonia gas you add oxygen gas, which is supplied from air. From air it is subjected to fractional distillation, and the pure air is the raw material, and ammonia is also raw material. It gets oxidized in the presence of platinum at a temperature of 500 Kelvin of 9 bars of pressure. Platinum or rhodium, RH is rhenium, platinum or rhenium or rhodium, whatever you take, then nitric oxide gas plus H2O is obtained. So you can balance the equation. If you want to balance it, like you can take, that is we have 3 oxygens. So I think if I am going to take 4 nitrogen, then I think I can take 4 over here, and we have 12 hydrogens, so take 6 over here, and here you can place 5. The reaction is balanced. Take this nitric oxide, it is further oxidized. This nitric oxide gas is further oxidized in the presence of oxygen to give the reversible reaction, that is nitrogen dioxide gas. Take this nitrogen dioxide gas and you try to add water, and when you add water you get HNO3 plus nitric oxide gas. So to balance the equation, I think if I am going to take 2 over here for 6 plus 1 7, so I think if I am going to take 2 over here, I think if I could take 3, if I am going to take 3 nitrogens, if I take 3 nitrogens, then maybe 1 nitric oxide if I take, then 6, and there are 2 hydrogens. Yes, 6 plus 1, yes, the reaction is already balanced, so nitric oxide is obtained, and this nitric oxide which is obtained here is again recycled. It is added with it is subjected to recycling, and it is again converted to nitrogen dioxide, and this nitrogen dioxide again it is used for preparation of nitric acid. So this last step is meant for some recycling process. So in this way we can prepare the ammonia through the Ostwald's process, and directly from the metal salts also we can prepare the nitric acid. So if you go to the chemical properties of nitric acid, you go to the chemical properties. If you go to the chemical properties of nitric acid, go to the chemical properties of nitric acid. So here what we are noticing here is, as I told you, nitric acid, because of its highest oxidation state of +5, it can behave as an oxidizing agent. It's a good oxidizing agent. So if it is acting as an oxidizing agent, all oxidizing agents are said to be reduced. So here if you go for nitric acid, I repeat, if you go for nitric acid, because it's a good oxidizing agent, it oxidizes. You take copper, and when you add nitric acid in the dilute state, then here you are going to get, that is cupric nitrate plus nitric oxide plus H2O. Suppose if I am taking, because it is dilute, if I am taking 8 hydrogens, then if I am taking 4 moles of oxygen, 4 moles of water, if you take, number of oxygens are balanced, 8 3s are 24, and we have only 2 nitrogens here. Then if I am going to take, because I need to take 3 here, if I take 3, then I think 3 2s are 6, then 3 coppers, and 3 2s are 6 nitrogens, and take 2 over here, 3 2s are 6, 6 3 is 18, 20, 24, the reaction is balanced, and you take 3 over here. That means copper solid dilute nitric acid 8 moles you are taking, and 3 moles of copper nitrate is formed, and 1 mole of nitric oxide is also formed. It's a good oxidizing agent. If it is a good oxidizing agent, its oxygen state is +5, copper here oxygen state is 0, and it is oxidizing the copper to +2, and by itself it is getting reduced. All oxidizing agents, they have to get reduced by themselves. So this is one reaction where you can take. So copper plus again nitric acid, that is concentrated if you take. So again you are going to get here cupric nitrate, copper nitrate plus nitrogen dioxide plus H2O. If you take, suppose if I am taking 4 moles, if I am taking then 2, I can take here. Then I think already we have 4 3s are 12 oxygens are there. I don't think that we need to disturb here, because here we have 4 nitrates, so obviously we have only 2 nitrates. So suppose if I am going to place 2 over here, might be the number of nitrogens are balanced. So if the number of nitrogens are balanced, the number of oxygens should also be balanced. So if we have 3 to the 6 oxygens, 6 plus 4 10, 10 plus 12, everything is balanced. So again this is copper solid, and here nitrogen, it is +5 oxygen state acting as oxidizing agent. So copper is 0, here the copper is +2, so it is oxidizing the copper from 0 oxygen state to +2 oxygen state. Because it is acting as an oxidizing agent, it has to undergo reduction, that is +4. So therefore this is with respect to copper. Likewise the nitric acid also can react with the, that is dilute nitric acid reacts with zinc solid, again zinc solid to give, that is zinc nitrate. We can take zinc nitrate plus nitric oxide plus H2O. If you take, I think if I am going to take 10 moles of nitric acid, then here I think if I am going to take 5, then 5 to 10 hydrogens, then we have 10 nitrates. 10 nitrates means like here we have 10 hydrogens and 10 hydrogens. Then we have number of nitrates are only 2. So if I am going to take 8 here, and if I am going to take 2 here, I think the reaction has to balance, because I am taking 8 nitrates. So this is okay. If I am going to take 4, 2s are 8 nitrates and 2 nitric oxides, I think the rest of the reaction has to balance automatically. So if I am taking total we have 10 nitrates here in the reactant side, and 10 hydrogens are already balanced. 10 3 is 30. So 3 2s are 6, 6 4s are 24, 3 2s are 6, 6 4s are 24, 24 plus 2, 26, 26 plus 5. There is a slight modification here, because 1 oxygen is coming extra. So what I am going to do is, because it is dilute, usually we say very dilute, so what I am doing here is I am going to remove this 2 as a coefficient and make it N2O. So that means in the dilute state, dilute nitric acid, when it is reacting with zinc, of course the number of zincs have to be balanced. So the molar coefficient of zinc is 4, here it is 10, here it is again 4, and here it is 5, and here it is 1. So the molar coefficient is 1. So dilute nitric acid, when it is reacting with zinc metal, it is forming zinc nitrate and nitrous acid. This nitrous acid is therefore, this is nitrous acid, and it is also called as laughing gas, and the reaction is automatically balanced. Now you take zinc and you add nitric acid, which is concentrated. If you are taking concentrated, so you are going to get here zinc nitrate and nitrogen dioxide plus H2O. If you take, then yes, we can balance the equation. I suppose if I am taking 4 here and take 2 over here, 3 nitrates are there, so take 2 over here, the number of nitrogens are not disturbed. 4th is a 12 oxygens. I think we have 6 oxygens plus 4 oxygens, 10 plus 2 12. Yes, everything is balanced. This is nitrogen dioxide gas. Yes, again here also the nitric acid is acting as an oxidizing agent. Here also it is acting as an oxidizing agent. It is +5, zinc is 0, then here zinc is +2, and because it is acting as an oxidizing agent, nitric acid acting as an oxidizing agent, it has to get reduced, so it is +1 oxygen state. Yes, here also it is oxidizing agent, so +5 oxygen state, here it is 0. So here if you go to the nitric acid, in the concentrate nitric acid acting as an oxidizing agent, yes, here also it is oxidizing agent, +5, zinc is 0, so here zinc is again +2, so it is oxidizing the zinc from 0 oxygen state to +2 oxygen state. Because it is oxidizing agent, it has to get reduced, yes, it is reducing, and because the oxidation number of nitrogen is +4. So all the reactions are properly justified. With respect to copper, here we have seen how the nitric acid is reacting with the copper as a metal, and here we have seen how the nitric acid is reacting with zinc as a metal. And one important point what we have to note down here is, that is noble metals like that is platinum and gold, because of their inert nature, they are stable, they are inert, unreactive. So therefore there is no reaction. Platinum, gold, when you are treating with concentrated nitric acid, no reaction, that means no action, because they are noble metals. Next is, similarly, if you go for iron, chromium, aluminium, these are some of the metals, iron, chromium, aluminium, they turn passive towards nitric acid. Passive to nitric acid, that means, what is the meaning of this? Actually, initially when nitric acid is treated with, for example, initially when nitric acid is treated with aluminium, this aluminium forms a protective layer. It forms a protective layer of aluminium nitrate, and once it forms the aluminium nitrate, any more addition of the nitric acid into the aluminium cylinders, you find that there is no reaction of nitric acid on the aluminium cylinder, so it becomes a protective layer. This is called passivity. In fact, the metals, that means once the aluminium nitrate is formed, it becomes a passive layer. This is called passivity on surface of container. The passivity is nothing but forming a protective layer. Yeah, already I have written here, forming of protective layer. That's why you can see that iron, chromium and aluminium, when they react with nitric acid, because of their passivity, it is not easy for the nitric acid to go and act on the metals like pure metals like iron, chromium and aluminium, because of the property of passivity. Then all these are the properties of nitric acid with respect to metals, how the nitric acid is going and acting on the metals, how the metals are trying to show the affinity towards the nitric acid and becoming different kinds of salts, and how the nitric acid is becoming the oxidizing agents when it is reacting with metals, we have learned. Now in the next part of the discussion, we are going to learn how nitric acid is going to become the oxidizing agent in the case of the nonmetals, that is nitric acid when it reacts with nonmetals, how do it behave and what kind of changes the reaction is going to take place in that changes. Let us try to observe. So suppose if you are going to see that what is the action of nitric acid on nonmetals, you know very well that iodine is a nonmetal, carbon is a nonmetal, sulfur is a nonmetal and phosphorus is also a nonmetal. So if you take this choice of nonmetals, then what we are noticing here is definitely nitric acid is an oxidizing agent, and it forms HiO3 iodic acid plus nitrogen dioxide plus water are the products which are obtained. Yes, we can balance the equation later, and here this is solid, and here if you take that is carbon, when it is treated with nitric acid, again it acts as an oxidizing agent. It converts the carbon to carbon dioxide gas, and it forms nitrogen dioxide gas, and it forms the H2O liquid. Then if you go for that is octatomic sulfur atomicity is 8, phosphorus atomicity is 4, and carbon atomicity is 1, iodine atomicity is 2. So therefore if you go for S8, it forms H2SO4, that is H2SO4, that is aqueous. We can take, then we can get nitrogen dioxide, and you can take water as a liquid. Fine, no problem. Then here we can take H3PO4 aqueous plus nitrogen dioxide gas plus H2O liquid. Fine. So that means in all the cases what we are noticing here is, let us try to balance the equation later. Here nitrogen is +5 oxidation state, and here iodine is 0. So here iodic acid, iodine oxidation state is +5, and nitrogen, yes, it has to get reduced, so it is +4. Fine. Here also nitric acid is plus 5 nitrogen, carbon is 0, here carbon is plus 4, and here the nitrogen dioxide is, in nitrogen dioxide nitrogen is plus 4. Again here sulfur is 0, again nitric acid it is plus 5, and here sulfuric acid it is plus 6. Yes, in nitrogen dioxide again it is plus 4. Again this is an oxidizing agent. Okay. Again if you go for nitric acid as an oxidizing agent, yes it is plus 5 oxidation state. Phosphorus is 0. Again here phosphorus is plus 5. Then here nitrogen dioxide it is plus 4. Yes, fine, no problem. So now how do you balance the equation? Because we have 10 nitrogens here. So definitely compulsory we have to mark here 10. Then thereby we have 2 iodines. So I think if I am going to mark 2 here, nitrogens and iodines automatically they have to get balanced. As of now we are getting 10 2s, 20 oxygens, and we have 2 3 6 oxygens, 26 oxygens are there. So we need another only 4 we have. So we have 10 because we have already 2 hydrogens. So if I am going to take 4 over here, yes, the reaction is already balanced. So just I am going to mark one line to avoid the confusion here. I am marking one line like this. Then you go for the second case. If you are going for the second case, you are noticing that yes, here we have 4 nitrates, that means 4 nitrogens are there. So take the molar coefficient as 4. I am taking the molar coefficient as 4. If I am taking the molar coefficient as 4, then you can find that here number of hydrogens are 4. So take 2 over here. So 2 as the molar coefficient. Yes, count the number of oxygens in the reactant side as well. 4 is the 12 oxygens. If you take here 4 to the 8 oxygens, 8 plus 2 oxygens, 10 oxygens plus 2 oxygens, yes, the reaction is automatically balanced. So that is over. Now go for the third case. In the third case, if I am going in the third case, if I am taking, you are finding that here 48 nitrogens are there. 48 nitrogens means I think there is no other nitrogen is there. So if I am going to take 48 over here, the number of nitrogens are balanced. Then I think we have 8 sulfurs are there. So suppose if I am going to take 8 sulfurs and nitrogens are balanced. But if you take 48 into 3, 8 4s are 8 is a 24, 2, 12 plus 2, 144. If you take 144 means 48 2s are already here in the case of, that is in the case of number of oxygens in the case of nitrogen dioxide. In nitrogen dioxide we have 96 oxygens are there. 96 oxygens are already there. Then in the case of sulfuric acid we have 8 4s are 32 oxygens are there. In H2SO4 we have 32 oxygens. 32 oxygens are there, and we have to balance the, so 32 plus 96. If you take 96 plus 32, if you take, this is 8 12 128, but we have 144. So 144 of 128 if you take, so this is 6 and this is 3, so this is 1. So therefore still we need another 16 oxygens are required anyhow, because we have 48 hydrogens are there. So 48 hydrogens means, we suppose if I am going to take over here, that is if I am going to take here, that is 16 I am going to take, because here already we have another 16 are there. So that is 16 means if I am going to take 8 here, so 8 means 8 2s are 16. Here we have 48 hydrogens, 8 here. So 16 2s are 32 hydrogens, and we have another 16 hydrogens. So 32 plus 16, yes, 48. Yes, the entire reaction is balanced altogether. At last we have balanced the equation. But this is very, very important reaction, because it is involved with more number of molar coefficients. So we should be a little bit careful in understanding the balancing of equation. Then if you go for the last case, if you are going for the last case here, you have 20 moles of nitric acid. In the 20 moles of nitric acid we have 20 nitrogens are there. So here let us take 20. So blindly I am going to balance the number of nitrogens, and we have 4 phosphorus atoms, so take 4 over here. Yes, number of phosphorus and number of nitrogens are already balanced. Then you go for 20 hydrogens. I think if I am going to take, because already 4 3 12 hydrogens are there, so 12 means I think I need to take another 4 only, another 8. So if I am going to take 4 over here, I think the number of hydrogens are also balanced. And if you check out the number of oxygens, if you take 20 into 3 60, So 16 minus 22 is 40 and we have 4 4s are 16, 56 plus 4 oxygen, 60 oxygens. Yes, the reaction is balanced. So in this way, the reaction we have to balance it one by one based on the technique we have to adopt. But only thing is that at least you have to remember how many number of moles you are adding for iodine, how many number of moles of nitric acid you are adding for iodine, how many number of moles of carbon you are adding for how many number of moles of nitric acid you are adding for carbon, how many number of moles of nitric acid you are adding for sulfur, how many number of moles of nitric acid you are adding for white phosphorus is we have to remember, so that we can easily I can identify and balance the rest of the reaction. So this is 48 moles, this is 48 moles, this is 4 moles, here 10 moles. So this is what you have to keep it in your mind. And this H3PO4 is phosphoric acid. H3PO4 is phosphoric acid. This is iodic acid. Here the last topic, that is brown ring test. So if you go for brown ring test, that is this brown ring test, it is a test for nitrate ions. It is a test for nitrate ions. So here what we are doing here is we take this nitrate ion, take the nitrate ion, and you take Fe2 plus ion, 3 moles of Fe2 plus ion plus 4 moles of H plus ions. If you take, it forms 3 moles of Fe3 plus ion plus nitric oxide plus 2 moles of water. You see whether the reaction, whether now this is acting as, in fact this ferrous ion is acting as a reducing agent. This ferrous ion acts as a reducing agent. It is reducing the nitrate ion, which is already in the +5 oxidation state. It is reduced to +2 oxidation state. So all reducing agents, they get oxidized. So what you are noticing here is this is nitrate ion, this is the nitrate, this is the nitrate ion. So this nitrate ion is being reduced to nitric oxide with ferrous ion. So the ferrous ion, so total number of charges, you concentrate properly, the total number of charges on the reactant side is, that is 3 2s are 6 positive charges and 4 positive charges, 10 positive charges with 1 negative charge. So that means in the reactant side altogether the net charge is 9 positive charges are there. Again in the product side also, if you take here carefully, this is the oxygen state, mind you should not get confused with this. This is the oxygen state of nitrogen and this is total charge. Again 9 positive charges. Yes, here in the product side also net charge is 9 positive charges. Fine. So take this, again take the nitric oxide, and you take that nitric oxide FeH2O taken 6 times of that is Fe2 plus, it interacts with the nitric oxide gas, again this, that is hexahydrate iron cationic complex, iron to cationic complex, it interacts with nitric oxide gas, and immediately it forms a complex, that is FeH2O taken 5 times of NO. It will become a neutral ligand which will satisfy the coordination number of the iron. The net charge remains as it is and it forms water. So this is going to become the brown ring complex for the nitrate ions. Actually, so here what we have to notice here is, Fe2 plus is a source of ferrous sulfate, and 4H plus ions are the sources of, that is sulfuric acid. So that means this ferrous sulfate and sulfuric acid, they are trying to act on nitrate. They are trying to act on nitrate, which is acting as a reducing agent, and it is converting, this nitrate is being reduced to nitric oxide, and they are giving rise to ferric sulfate plus H2O. This is the possible reaction. Of course, I am not balancing the reaction, and the brown ring is found between these two layers. Between the brown ring is obtained between the sulfuric acid and ferrous sulfate. A brown ring is obtained. The brown ring formation of the nitrate is because of the formation of this complex. So the next part of the discussion is phosphorus. Phosphorus, its allotropy and its compounds. Usually if you take white phosphorus, whether it is phosphorus, if you take phosphorus, symbol is P4, that means its atomicity is 4, and this phosphorus, this P4 in its allotropy, if you go into the allotropy, it exists in two forms, that is white phosphorus and the other one is red phosphorus. White phosphorus is highly unstable, reactive, most reactive, that is insoluble in water, but soluble in carbon disulfide solvent, and it readily catches fire. And if you go for red phosphorus also, it is actually obtained. Red phosphorus is actually obtained from white phosphorus by heating it to a temperature of 573 Kelvin. You can get red phosphorus. Yes, it is. If you go for if you go for white phosphorus, it is very harmful in nature. So it is harmless. And you find it is less reactive, as in the case of in the case of white phosphorus, it is harmless. It is insoluble in carbon disulfide also, and also water. It is insoluble in carbon disulfide as well as water. It is less reactive. Because of its layered structure. And here you can add one more. It is most reactive because of the tetrahedral geometry, tetrahedral nature, and also angle strain, which is equal to 60 degrees. So all these points can be compared and contrasted. So if you go to the white phosphorus, if you take, it is tetrahedral in nature, like this you can take the white phosphorus. So the bond angle is around 60 degrees. This is white phosphorus, tetrahedral, P4 white. This is tetrahedral in shape. And if you go for red phosphorus, it is layered structure. It has layered structure like this, polymeric layered structure, and so on. This is P4 red phosphorus. It has layered structure. If you go to the reactivity of white phosphorus, actually this white phosphorus is highly reactive, so it reacts with NaOH in the presence of water under dilute conditions. It gives NaH2PO2 plus pH3. Actually this reaction significance is white phosphorus is undergoing disproportionation reaction. So here white phosphorus oxygen state is 0. Here the sodium dihydrogen phosphite, its oxygen state is +1, and this is phosphorus is -3. So it is somewhat, the reaction is undergoing disproportionation reaction, and this is a poisonous gas, that is phosphine. It's a poisonous gas, and this reaction, it shows the disproportionation disproportionation reaction wherein which the phosphorus is undergoing both oxidation as well as reduction. It is getting oxidized in the form of sodium dihydrogen phosphide and it is getting reduced in the form of phosphine gas. So the disproportionation reaction is very clearly seen in that step.